Welcome to AI Frontiers, where the wild, ever-evolving world of artificial intelligence is unraveled through groundbreaking research. This episode dives into robotics revolution, AI-powered machines in action, synthesizing 45 papers from the arXiv preprint server dated September 22, 2025, all under computer science robotics. This presentation overviews the magic of AI in robotics. A dive is taken into 45 papers from one explosive day in robotics research. The journey proceeds from field basics to themes, findings, and future visions. A spotlight is placed on 3 standout papers as the papers of the day. An engaging narrative blends technical insights with real-world impact. Preparation is advised for a conversational tour of robots reshaping the world. Computer science robotics, often tagged as cs.RO on the arXiv preprint server, represents the thrilling intersection where algorithms meet metal and motors. Robotics blends algorithms, machine learning, and hardware for physical interaction. Focus is placed on sensing, decision-making, and action in dynamic environments. Key applications include manufacturing precision, healthcare assistance, and extreme exploration. Challenges like uncertainty, safety, and human collaboration are tackled. These 45 papers showcase vibrant innovations enhancing robot resilience and efficiency. From sifting through these papers, 5 overarching themes capture the pulse of current robotics research, though this slide highlights 3 dominant ones emerging from the papers. A key theme is locomotion in challenging environments, adapting to terrains like ice or forests. Another focuses on dexterous manipulation for precise object handling without grasping. The third emphasizes perception and sensing under uncertainty for reliable autonomy. Themes interconnect, boosting overall robot intelligence and adaptability. These are supported by evidence from papers like Kamihara et al. On bipedal control. Theme 1 centers on locomotion and challenging environments, navigating tricky terrains with AI. Robots adapt to slippery slopes and uneven stairs using hybrid controls. Kamihara et al. Combine reinforcement learning with model predictive control for safer bipedal walking. Drones optimize trajectories in GPS-denied zones per Chen et al. This enhances applications in search and rescue and planetary exploration. The technical concept involves reinforcement learning, where agents learn optimal actions through trial rewards, improving adaptability. Theme 2 addresses dexterous manipulation and object handling, achieving human-like precision in grasping and pushing. Focus is placed on non-prehensile actions like pushing with multi-fingered hands. Li et al. Use geometry-aware models for stable object manipulation. This includes dynamic handovers and tactile feedback for delicate tasks. It proves vital for home robots or ecosystem restoration, like handling coral. The technical concept features diffusion models, which generate varied outputs like hand poses mimicking creative human problem-solving. Theme 3 explores perception and sensing under uncertainty, interpreting messy real-world data. Robots process occluded or faulty sensor data for reliable decisions. This involves radar point clouds and fast LiDAR simulations. It supports human-robot collaboration with haptic and VR learning. Examples include fault detection via counterfactual reasoning. Integration occurs with planning for smarter, privacy-aware AI decisions. Key findings reveal groundbreaking insights across the papers. Reinforcement learning model predictive control hybrids reduce bipedal falls by 50% on slippery terrains, as shown by Kamihara et al. Mutating rewards in reinforcement learning uncovers new skills like liquid mixing automatically. RGB-only perception enables near-perfect dynamic handovers, per Li et al. GPU-accelerated LiDAR hits 500 frames per second, bridging sim-to-real gaps. Pre-training on videos yields zero-shot robot generalization, cutting data needs. Methodologies synthesize common approaches in the papers. Reinforcement learning involves trial and error for dynamic tasks, strong in uncertainty but compute-heavy. Model predictive control optimizes trajectories with constraints, ensures safety but needs hybrids for unknowns. Diffusion models generate diverse poses or plans, data-intensive yet versatile for multimodal tasks. Multimodal fusion combines vision, touch, and human data for imitation learning. Quick but faces syn-to-real gaps. The first selected research paper is by Kamihara et al., titled RL-augmented Adaptive Model Predictive Control for Bipedal Locomotion over Challenging Terrain. It is selected for its innovative hybrid approach enhancing safety and adaptability. The method hybridizes reinforcement learning and model predictive control to adjust gaits on ice or stairs, reducing falls. Testing occurs in simulations, showing emergent behaviors like cautious steps. The impact revolutionizes humanoid robots for disaster response. Novelty lies in merging learning flexibility with control reliability for real-world terrains. The second selected research paper is by Lee et al., titled Learning Geometry-Aware Non-Prehensile Pushing and Pulling with Dexterous Hands. It is chosen for advancing dexterous, non-grasping manipulation in confined spaces. Diffusion models are used to predict optimal hand poses from object geometry. High success is achieved in real trials across hand types and irregular objects. Representativeness pushes boundaries for versatile home and warehouse robots. The impact enables precise handling of awkward items, reducing reliance on grippers. The third selected research paper is by Chen et al., titled RO-MPPI, Anchor-Guided Ensemble Trajectory Optimization for Agile Mapless Drone Navigation. It's selected for enabling fast onboard navigation in cluttered environments. Ensemble model predictive control with anchors from LiDAR is employed for collision-free drone flights. Speeds of 7 meters per second are achieved with 80% success in real tests. Novelty features GPU parallel optimization for agile mapless autonomy. Representativeness addresses perception challenges in GPS-denied zones like forests. Future directions outline next steps in robotics research. Advances in edge AI are expected for real-time onboard processing in drones and humanoids. Integration of multimodal data like vision and language will enable zero-shot learning. Focus will be placed on ethical, sustainable designs for conservation and privacy. Sim-to-real gaps will be bridged with digital twins and uncertainty models. Challenges in safety for healthcare and energy-efficient manufacturing will be tackled. This synthesis was created using AI tools including GPT-Grok using model Grok-4-0709, TTS synthesis using OpenAI, and image generation using Google. While the synthesized content underwent review by a human expert, it is important to acknowledge that some oversights may still exist. All the references are provided. Tools enabled cohesive narrative from 45 paper summaries. Focus is placed on distilling themes and findings for broad accessibility. Subscription and channel information invite joining the AI Frontiers community. Subscription to the YouTube channel is encouraged for more research deep dives and updates. The channel title is AI Frontiers. The description emphasizes staying ahead in AI and robotics. Hit subscribe now. Thoughts on these robotics breakthroughs are welcomed to be shared. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.